Hello, welcome back to LFI Educates. Today we are going to study combination of cells. That is, in chapter 3 we are studying current electricity. Now, in earlier classes you learned about combination of resistors, combination of capacitors. Why do we combine? You have the idea already. That idea you have. Now, in this case also we can combine the cells in two types. One is called series connection, and the other one is called parallel connection. In this connection, all the terminals, positive ends will be on one side, and all negative terminals will be on the other side, or we call it as end-to-end connection also. Like this, negative terminal of one cell connected to positive terminal of the other cell. Again, negative terminal of the second cell connected to positive terminal of the third cell, and so on. All the polarity you can see, positive will be on one side, and negative will be on the other side. Now you will be reading this, or you will be studying these cells in series in two phases. One is that when the cells are identical, there will be n identical cells. Each of EMF epsilon and internal resistance R. Let the cells be connected to an external resistance R, capital R. Let the external resistance be connected in the circuit, or let R be the, you can write like this, R be the external resistance. This way you can take it. Now what you have to do is, you have to find out the equivalent EMF of the cells. Equivalent EMF, how will you find out? Equivalent EMF of n cells is equal to, you have to think, these cells are connected in series. In series connection, the EMFs will be all different. The current remains the same, and the EMFs will be all different. We'll have to add them up. But as we're taking all of them to be equal, epsilon, so you'll go on writing like this, epsilon plus, like this up to n times, because we have n identical cells. So if you sum up epsilon plus epsilon up to n times, it will give us n epsilon. So this will give us the equivalent EMF of n cells in series. Now let us find out the equivalent internal resistance, equivalent internal resistance of n cells in series. This also you already know that when resistors are connected in series, the equivalent resistance is sum of the individual resistances. So here also you write R to n times. So ultimately here also you get n times R. Now, if you look at the circuit diagram, then you can find one more resistance is there. That is your external resistance. So, the overall circuit, the total resistance will be the external resistance plus the equivalent resistance of all the internal cells. So, the equivalent resistance of the whole circuit, equivalent resistance of the circuit will be the sum total of R plus NR. You may be thinking why it's added up, because together if you consider it as an equivalent cell, a single cell, it will look like this. This is your external resistance current will flow in this direction. This is your equivalent EMF, and this is your equivalent internal resistance, EQ, REQ. So this resistance and this resistance, again they are in series. That's why it's being added up, R plus NR. Once you know the total equivalent resistance in the whole circuit and the total EMF of N cells, then you can find out the current that the external resistance draws from the cell. So I'll write here the current drawn by the external resistance, or the total current drawn by the external resistance R is I is equal to the potential, that is the equivalent EMF, that is N epsilon divided by the equivalent resistance of the whole circuit, that is R plus NR. This will be the amount of current drawn by the external resistance when N identical cells are connected in series. Here some cases will arise. Let us see the special cases. Case 1. When the external resistance is less, much less than the internal resistances, that is NR, then the current drawn from the cells I will be, if capital R is very much less, then the current drawn will be, this will be neglected, then we will have N epsilon divided by NR, then we will get epsilon divided by R. So it will be equivalent to the current drawn by a single cell. This is epsilon and this is R. Current drawn by a single cell. Now when we see the second case, case 2, let us see. In this case, suppose when the external resistance is much bigger than the internal resistance, then you will get something else. It will look different than this. What you get here is I is equal to N epsilon divided by R. This time the internal resistance will be neglected. In this case, you will find that it is N times the current drawn by a single cell. This is N times the current drawn by a single cell. So now it is your choice. Now if your external resistance, what you are going to use, it will depend upon that. If the resistance is very high, then it is wise to connect in series. You can see here, if the external resistance is very large, then the current that you can draw from the cell is N times. Means suppose 10 cells you are using, 10 times the current drawn by a single cell. If a single cell, from there you are drawing suppose 5 ampere of current, then in 10 cells you will get 5 into 10, 50 ampere of current, you will get it. So whenever it will depend upon its external resistance. So whenever you want to connect them in series, you should know that the external resistance must be very, very high. If the external resistance is less, then what happens, you can see here in the first case, if the external resistance is less, then the current drawn is equivalent to a single cell. That means how much current you get from a single cell, that only you get it even if you connect number of cells together in series. Now let us see the second topic, that is our cells in parallel. type of connection, that is cells in parallel. Here also I am taking a number of cells. So this time it is m cells, suppose I am taking, each of same EMF epsilon, epsilon, epsilon. Then the internal resistances, as we are doing for identical cells, let us take it as R. Here also let us take it as R. Here also let us take it as R. Now in parallel connection, as you know, all the positive terminals all has to be connected at one end. Let us say this is the point we are connecting it. Like this. And here also one external resistance, let us take it as R, capital R. In this case, suppose these two are connected at two fixed ends, A and B. We know that potential across the cells will remain the same if they are in parallel connection. So in this case, we are taking n cells here, connected in parallel. So here also, like the earlier one, you can write down that m identical cells be connected in parallel with EMF or EMFs epsilon and internal resistance R. Also let the cells be connected to the external resistance, capital R. Now here also you will find out the equivalent EMF, and as they are connected in parallel, we know that the EMF will remain the same. So we write down equivalent EMF of n cells. So here it will remain as epsilon only, because all of them will have the same EMF. Then we will find out the equivalent resistance of n cells in parallel, that you already know. The reciprocal of the resultant resistance is equal to the sum of the individual reciprocal of the individual resistances. So equivalent internal resistance of n cells, like this we'll find out 1 by Rp is equal to 1 by R1 plus 1 by R2 plus it will go up to 1 by Rn, as we have n cells. But now R1, R2, R3 as the cells are identical, so it will be 1 by R plus 1 by R plus 1 by R. Everywhere it will be 1 by R plus 1 by R plus 1 by R plus 1 by R. How many times? Then we'll say m times, because n cells are there. So we'll write to m terms. So ultimately what we get here is 1 by Rp is equal to 1 by R plus 1 by R plus 1 by R up to m times it will be m by R. So your equivalent resistance, internal resistance will be R by m. After you find out the equivalent internal resistance and the equivalent EMF, your circuit will look somewhat like this. Here the current will come from positive to the negative end. So equivalent cell will look like this, with epsilon equivalent and internal resistance R equivalent, and then your external resistance R. Current will be flowing this direction from positive to negative terminal, from higher potential to lower potential. So now, what will be the equivalent resistance of the whole circuit? This is your equivalent resistance. You got R by M. This is your R by M. So you have to add them up. Equivalent resistance of the circuit will be external resistance plus the equivalent internal resistance, that is R by M. R by M. So after knowing this equivalent resistance for the whole circuit and the equivalent EMF of all the cells, that was epsilon, you can find out the current drawn from the cells, or we can say the current drawn by the external resistance. You can write down like this. Therefore, current drawn by the external resistance R is I is equal to, your EMF was epsilon and your overall resistance is R plus R by M. So this is the expression, you can get it, the amount of current that you can draw from all the cells. Now here also, like the earlier case, we have two special cases. Case 1, let us see, when external resistance is very large compared to the equivalent internal resistance, then what will happen? You can see from the expression I is equal to, if R is very large, epsilon divided by R. So it is current drawn by a single cell. By a single cell. Now the second case, case 2, when R is very less as compared to the equivalent internal resistance of the cells, then current I is equal to, this time R is very less, so it will be epsilon divided by R by M. It will become M times epsilon by R. It is M times the current drawn by a single cell. M times the current drawn by a single cell. Now in this case, what we'll have to know is, suppose you have equivalent cells, you want to connect them in parallel, then you must make sure that the internal resistance is the external resistance is very less, then it is profitable. If the external resistance is very less, then there is an advantage of connecting it in parallel. The current drawn will be more, it will be M times. M times means, suppose 10 cells are there, then it will be 10 times the current that will be drawn by a single cell. So after learning these two combination of cells in series and in parallel, now if I ask you, how will you connect the cells? Will you connect it in series or in parallel? If the external resistance is very high, then you should know that I must connect in series. And if the external resistance is less, then how you are going to connect the cells? Then you should know that I have to connect it in parallel. That idea you can get it from here. And these properties are used to make battery. We know inverter batteries that we use, car batteries and all, there more than one cells are there. Then we call it as battery, combination of two or more than two cells. So now, for what purpose you are going to use the battery? Depending upon that, you can connect the cells. Now let us see the third topic, that is mixed grouping of cells. Mixed grouping of cells. Let there be n cells in each row and m cells, or we can say m rows. We'll take like this. Here I'll draw the figure. Suppose there are n cells like this in each row, n cells, and altogether you have m rows. M rows. Let us connect them in parallel. Like this. All of them are connected to two endpoints here and here, and then one external resistance. Let us take it as R. Each has an EMF epsilon and internal resistances R. All the cells are identical. So in this case, what you do is, first of all, for each row you find out the internal resistance and the internal equivalent resistance and equivalent EMFs. Like this will start. Equivalent EMF of each row, it is equal to R plus EMF we are talking about, epsilon plus epsilon plus epsilon plus epsilon to n times. So it will become n times epsilon. Like that, equivalent internal resistance of each row, because they are connected in series. So it will be R plus to n times. So it will become n times R. That is for each row. After you do it for each row, your circuit will change like this. You follow the equivalent EMF and equivalent internal resistance. So it will look somewhat like this. Everywhere you got NR, and here N epsilon, N epsilon. This way you think, as they are connected in parallel. This is the external resistance, capital R. Like this. Current is flowing this way. So now, after grouping them together, it looks like as if they are connected in parallel. Not as if, it is connected in parallel. So the equivalent internal resistance of the whole circuit, the equivalent internal resistance of the circuit, let us first find out. 1 by R equivalent is equal to 1 by NR plus 1 by NR plus how many rows are there, then you know there are m rows. This is m rows. So it will be up to m times. So you get like this, m times 1 by nr or m by nr. So in this case, R equivalent, if you take the reciprocal, it will become nr divided by m. So this is the equivalent internal resistance of the circuit, and equivalent resistance of the whole circuit, not only the internal resistance, this external resistance also if you take, you have to add them up. Capital R plus nr by m. So equivalent resistance, not the internal alone, for the whole circuit, for the circuit, it will look like this. It will be R plus the external resistance plus the equivalent internal resistance, that is nr divided by m. Now you got the equivalent resistance for the whole circuit. Now let us find out the equivalent resistance, equivalent EMF of the cells. The equivalent EMF of the cells, now they are connected in parallel. In parallel it will remain the same. It is earlier what we found out, n times epsilon, it will remain like this. So now by using these two, you can calculate the amount of current that can be drawn from the cells. The total current drawn, the current drawn by the external resistance R is I is equal to your EMF, equivalent EMF divided by equivalent resistance for the whole circuit. With this you can calculate the amount of current that can be drawn by mixed grouping of cells. Here one point to be noted: if you do mixed grouping of cells, then the current that we can draw is maximum if, this is the condition you have to know, if the equivalent EMF internal, the equivalent internal resistances and the external resistance, if both of them are equal, it's like this. If R is equal to nR by M, then maximum current can be drawn from mixed grouping or mixed combination of cells. It is like this. Now let us discuss about this combination of cells when the cells are not identical. Here first of all let us say about cells in series. Now if the cells are not identical, let us take this way. For series, let us see first. Then here the EMF of the first cell, let it be epsilon 1 and the internal resistance R1, and EMF of the second cell as epsilon 2 and internal resistance R2. Let us assume like this. Here if the cells are in series, then the equivalent EMF, E equivalent, it will be E1 plus E2, epsilon 1 plus epsilon 2, and R equivalent, it will be R1 plus R2. If you can remember this, you can solve the numericals, but you may be thinking, how did we get this? To know this, you will have to do it using Kirchhoff's rule that we have done earlier. Let us take this terminal as point A and this terminal as point B, and let the current flow in this direction, because both the positive terminals are facing this side, left side. Then where to go the current? It has to complete the circuit. So to complete the circuit, you can take an external resistance R here, and then it will enter through this point B, like this. It will enter this way. So if you use Kirchhoff's rules, then you come to know that how we get this equivalent EMF as epsilon1 plus epsilon2. Let us choose the path. This side is higher potential, this side is lower potential. Let us choose the path from higher potential to lower potential like this. Then we will write like this: VA minus VB is equal to the EMFs. Let us see first here. It is from positive terminal to negative terminal. So it will be epsilon1, it will be positive. It is going from positive to negative. The second one, epsilon2, also it is from positive to negative. So I'll write it as plus epsilon2. But whereas the internal resistance, the current that is flowing, suppose it is I, then this side also the current flowing will be I, because it will enter, the same current will enter as they are connected in series. So the product of current and resistance, if you look, is opposite to the path that we have selected. It's going in the reverse direction. So I'll write here minus I R1 across this resistance R1, and across this resistance R2 also current I is flowing, and its direction is opposite to the path that we have selected. So I'm writing it as minus I R2. So what happens here is the difference in potential, we write it as V. This is epsilon1 plus epsilon2. Let us take it together like this. Minus, you can take common. I is common. So it will be R1 plus R2. Now let us mark this as equation number 1. Then if we use our relation between EMF and potential difference, we know that V is equal to E minus IR. Here E will indicate E equivalent, R will indicate R equivalent. Then if you compare these two equations, then you get the equivalent EMF as epsilon equivalent. We get the equivalent EMF E equivalent as, if you compare it, you will get it epsilon1 plus epsilon2. And R equivalent, you will get it as R1 plus R equivalent, you will get it as R1 plus R2. Like this, you can get the equivalent values of EMF and equivalent values of resistance. But now, if the cells are changed, one of the polarity is changed, suppose. Now, if I say equivalent, what does it mean here? Here it will look like this. This is EMF equivalent, and this is internal resistance equivalent. So two will group together as one, and internal resistance also will group together as one. But if the polarity is changed, in the second case, if suppose this is the positive polarity, like this, and one cell, the terminal has changed. Suppose this side became negative and this side is positive. It is still in series connection, but the polarities are not the same, not pointing in the same direction. Then what you will do is, suppose this is epsilon1, this is epsilon2, R1 and R2. In this case, the total equivalent epsilon equivalent will be, the total equivalent EMF will be E1 minus E2, epsilon1 minus epsilon2. Like this we will take it, but you need to be careful here. If epsilon1 is greater than epsilon2, if epsilon2 is bigger than epsilon1, or the EMF of the second cell is bigger than the EMF of the first cell, it will become reversed. Epsilon 2 minus epsilon 1. Then in that case, this is bigger. The second cell has more EMF than the first cell. If you look here carefully, you'll get the idea. If the polarity is reversed, this one if you are taking it as plus, then the next one will become minus. From there you can come to know that the equivalent EMF will be E1 minus E2. Then the equivalent internal resistance will remain the same. There will be no change. It will remain the same even if the polarity of the cells are reversed. Now let us discuss about the cells in parallel. If the cells are in parallel with different EMF and different internal resistance, then what will be the case? Let us see. This is your external resistance R, the EMF of the first cell E1, EMF of the second cell E2. This is internal resistance R1 of the first cell. R2 is the internal resistance of the second cell. In this case, the equivalent EMF, epsilon equivalent, will be equal to EMF of the first cell divided by R1 plus EMF of the second cell divided by R2 divided by 1 by R1 plus 1 by R2. This formula you have to keep in memory for doing the numericals. Then R equivalent, to find out 1 by R equivalent, it is 1 by R1 plus 1 by R2. These are the things we should keep in mind. Now let us see how do we get this equivalent EMF and equivalent resistance when the cells are connected in series. Here we have to apply Kirchhoff's rules like as we applied it in series. Here let us say that this cell is giving us current I1 and this cell is giving us current I2. So I1 and I2 by mixing together it is supposed to say I. Then this current I will flow across this external resistance, then it will come here I. Here it will be I1 and here it will be I2. Again will get distributed so that on the top the first cell will get the current I and the second cell will get the current. First cell will get current I1 and the second cell will get the current I2. Like this you can do. Here I is equal to I1 plus I2 using Kirchhoff's voltage law. Sorry, using Kirchhoff's current law. Kirchhoff's current law KCL. Now after doing this, let us choose this path. This one let us mark it as A. Let it be X, this point. Let this point be Y and let this point be P. And downside let us take like this. Let us take it as P this way. Generally we choose the path from left to right. So here potential across A and B, we will write it as VAB. VAB is equal to, or VA minus VB, write down first. VA minus VB. Then I use the rule. The path is this side. The terminal of the cell is from positive to negative. We are taking it as positive from before. So it will be epsilon 1. Then current and resistance. Here current is I1 and resistance is R1. But the direction of current is opposite to the direction of the path that we have chosen. So it will be minus I1 R1 minus I1 R1. So the potential we write as VAB or simply V. This is epsilon 1 minus I1 R1. This one I am bringing towards my left. So it is I1 R1 is equal to epsilon 1 minus V. So I1 is equal to epsilon 1 minus V divided by R1. Like this, find out the current I1. After finding out current I1 in the path, which path did we choose? AXYB. I can write here like this for path AXYB. After doing this, we'll go to the next branch, that is APQB. This way, the same path we are choosing, this way from left to right. So now I'll write VA minus VB is equal to, here also the same story. So directly you can write down for the path APQB. I can write like this for the path APQB. I'll get the same thing. I2 is equal to epsilon 2 minus the potential V divided by R2. Let it be question number 3. This one is 2. Now this I1 and I2, if you put it in this equation, if I mark this as equation number 1, putting the values of equation, or we can write putting the values of I1 and I2 in equation 1, we get I is equal to I1 plus I2, will edit these two, epsilon 1 minus V divided by R1 plus epsilon 2 minus V divided by R2. Now let us separate them into parts. Epsilon 1 by R1 plus epsilon 2 by R2. Minus, here both are minus, V is common, so I am taking V common. Then here I will get 1 by R1 plus 1 by R1 plus 1 by R2. Now this term, if I bring this side, this is I. This term, minus term, if I bring towards my left, it will be V into 1 by R1 plus 1 by R2. Then this is plus, this is equal to epsilon 1 by R1 plus epsilon 2 by R2, plus I will become minus I. Now this term as a whole I will bring down for both the terms. This one I will take it as one term. So V is equal to epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 by R1 plus 1 by R2. This one I am bringing down, minus I times I into 1 by R1 plus 1 by R2. Now comparing with the standard equation, V is equal to epsilon minus I R, this is effective, R effective. If you make it as equation number 5, comparing equation 4 and 5, what you will get is effective EMF, the resultant EMF is equal to epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 by R1 plus 1 by R2, and this will be your effective or the equivalent resistance. R effective is equal to 1 by R1 plus 1 by R2. This we can write it as 1 by R effective is equal to, reciprocate it, 1 by R1 plus 1 by R2. You can see here 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Like this you will get it. Now this effective you can write, or you can write it as equivalent. It's up to you. Meaning is the same. You can write it as equivalent as well. Now here also the same story. In this case, equivalent EMF, here it can be plus or it can be minus, depending upon whether the EMF E1 is bigger or E2 is bigger. If E1 is bigger, then here it will be plus, smaller one will be minus. And if E2 is bigger, then here it will be epsilon 2 by R2 minus epsilon 1 by R1. This will change. Whereas this effective or equivalent resistance will remain the same. Now let us do some numericals and see. The circuit in figure shows two cells connected in opposite to each other. Negative terminal is connected to negative terminal of the other cell. Cell E1 is of EMF 6 volt. E1 is of EMF 6 volt. And internal resistance 2 ohm. Internal resistance is 2 ohm. The cell E2 is of EMF 4 volt. It is of 4 volt. And internal resistance 8 ohm. Find the potential difference between the points A and B. Now to find out the potential difference between A and B, we have to know the total current, how much current is flowing. And to know the total current, we have to find out the effective resistance and the effective EMF of the cells. So let us first find out. Solution you write like this. Epsilon 1, or it's written here E1, the same thing. Epsilon 1 is equal to 6 volt. Epsilon 2, the EMF is 4 volt. Then you have internal resistance R1 is given here for cell E1, it is 2 ohm, and R2, the second cell, has internal resistance of 8 ohm. So to find out the equivalent EMF or the effective EMF when the cells are in opposition, negative is not connected to positive, it's negative connected to negative. You have to do E1 minus E2 as I said earlier, but we have to check it whether which is bigger. Here we can see 6 volt is bigger than 4 volt, so I'll do E1 minus E2. If this is 4 volt and this one is 6 volt, then we'll do E2 minus E1. But in this case, we'll do epsilon 1 minus epsilon 2, and it gives us 6 volt minus 4 volt is equal to 2 volt. So this is the equivalent EMF. Then let us see the equivalent resistance. Equivalent internal resistance is equal to, as the cells are connected in series, so you have to use your formula R1 plus R2. R1 is of 2 ohm and R2 is of 8 ohm. You are going to add it. 8 plus 2 is 10 ohm. Then the current flowing through the circuit you can find out. To find out the current I, we will do equivalent EMF divided by equivalent internal resistance. This is equivalent EMF is 2 volt and equivalent internal resistance is 10 ohm. So you get 1 by 5, that is 0.2. SI unit of electric current is ampere, so you write 0.2 ampere. After getting the current, then you can go for finding out the potential difference between the points A and B. Like as I have told you earlier, in Kirchhoff's laws, to find the potential between 2 points, you choose one path, and generally we are choosing from left to right. So just choose it from left to right, and then you start from A. potential at A, VA minus, we are going from left to right, VA to VB, that VA minus VB is equal to the potential first of the cell. Let us see, it is going from negative to positive. When you go from positive to negative in a cell, we are taking it as positive. So if it is going from negative to positive, we will take it as negative. Minus to plus, we will take it as negative. Minus 4 volt, minus 4 volt. Then the current, in which direction it is flowing. This arrowhead shows that it is flowing in this direction, opposite to that of the path that we have selected. So current direction and the path, if they are opposite to each other, we take it as negative. So current here it is 0.2 ampere, it will be negative 0.2 ampere. And what is the internal resistance of this cell from from A to B, or we can say the internal resistance of the cell? How much it is? This is cell, second cell internal resistance is 8 ohm. So 0.2 I into R is 8 ohm. Then now we calculate it. This is together it will give you volt. Minus 4 volt minus 1.6 volt. You will get here minus 5.6 volt. So potential difference between A to B, we got minus 5.6 volt. This shows that B is at a higher potential than A. You can keep it like this. Potential difference from A to B, it is minus 5.6 volt, or you can write VB minus VA. If you change this polarity, minus to plus, plus to minus, then this one also will become minus to plus. That means B is at a higher potential compared to A. Like this you can do the solution. Let us see one more question. So let us solve this question and see. Two cells of set EMF epsilon but internal resistance R1 and R2 are connected in series to an external resistance capital R. What should be the value of R so that the potential difference across the terminals of the first cell becomes 0? Here when the potential is 0, what is the value of R, they are asking you. So to start with, we'll find out the equivalent EMF. This time the EMFs are equal, so you don't have to subtract. For equivalent EMF, when they are connected in series, if they are identical, then we add them up, it will be 2 epsilon, and the equivalent internal resistance, it is R1 plus R2, but it is connected to this resistance R, so they are all in series. So we'll do R1 plus R2 plus R. In the whole circuit, the equivalent resistance will find out. And after knowing these two, you can find out the current drawn by the external resistance. I is equal to the total or the equivalent EMF, that is 2 epsilon, divided by R1 plus R2 plus R. Like this, you can find out the amount of current flowing across the circuit. Now, after doing this, to find the potential difference across the first cell, across this cell, let, like this you can assume, let V1 be the potential difference across the first cell. If you assume like this, you can take this relation V1 is equal to epsilon for the first cell minus I R1. Then you can put the value of I here, and the question says that the potential difference across the cell is 0. So according to the question, this is 0 is equal to epsilon minus I value. If you put 2 epsilon divided by R1 plus R2 plus R multiplied by R1. Like this you can write down. After writing this, you can transpose it by transposition. You can write it as minus term, you can take it towards your left, or this one you can take it towards your left. Epsilon is equal to 2 epsilon R1, 2 epsilon R1 divided by R1 plus R2, R1 plus R2 plus R, the external resistance. This epsilon, if you bring down, epsilon divided by epsilon is equal to 2R1, R1 plus R2 plus R. These two, if you cancel it, you get 1, then cross multiply. 2R1 is equal to R1 plus R2 plus R. So R will be equal to 2R1 minus R1 will be R1 plus R2. If you bring this side, minus R2. So you can get the expression for R in terms of R1 and R2. So this is your final answer. The resistance, the external resistance R will be R1 minus R2. Thank you and have a nice day. Stay tuned with LFI Educates.